the pointing to the increasing direction. All right, because the levels are increasing here. If I'm looking at a different point and I want to see U minimal, it has to be orthogonal to the level curve and it is pointing to the decreasing direction. All right, so these are pretty naturally defined coming from the gradient vectors. All right, so this is one of the applications we have for computing the derivatives. The other application we have is so-called linear approximation and tangent lines. So if I have a function f x, y, z is equal to 0 in the implicit form, we can compute the tangent plane equation, all right, at a point x0, y0, and z0. So you compute the partial derivatives fx, fy, and fz, and that is essentially the normal vector for the tangent plane. So you can have the tangent plane equation for the function in the implicit form. We also have z is equal to f of xy as the explicit form. We can use the partial derivatives to do linear approximation. So essentially saying I can compute the partial derivatives to get a total differential if you still remember the notation. The total differential is equal to fx dx plus fy dy. So we can use this total differential to approximate the change in the dependent variables. Don't be scared about this additional terminology here. The only thing I'm saying here is I can write down the linear form as here Lxy is equal to fx0 y0 plus fx at x0 multiplied by x minus x0 plus fy x0 y0 multiplied by y minus y0. So I can use the total differential as the difference of the function values, which means I can have this linear form to approximate my function at this given point. All right? So if I want to approximate a function by the total differentials, the only thing I need to do is to compute this linear form at a base point and then plug in these partial differentials and then evaluate. All right? Questions? So this is what we need to do. And the very last thing about applications involving partial derivatives is what we talked about last week. Finding the critical points and using the second order derivative test to classify the critical point. All right? And one of the applications coming from there, if you still remember, is to find the closest distance. Right? So if you still remember the question I gave you, so this is a plane. I need to find the closest point to the point 1, 2, 3, for instance. Right? So I want to find the point on the plane such that it is closest to a fixed point 1, 2, 3. Then you need to minimize the distance square. Right? You need to minimize the distance square between the points here to the point right here. Right? And then you need to eliminate one of the variables to get a minimizing question involving two independent variables. Okay? So the very last remark I want to make is the first midterm and throughout the whole semester, the questions are extremely similar to the online questions. Okay? Indeed, I will pick some identical questions into the midterm. So the online questions, and also there are sample tests and sample quizzes available over there. Practice and get your skill practice. Okay, so this is the skill test. You should be able to do partial derivatives and apply them quickly, and that's all. Okay, so I have all the spaces available, which means you don't need to prepare your own papers. Okay, if you need any additional scratch paper, I will also have that available, so you don't have to bring anything. Calculators and all the electronic devices are not allowed, and it's just